So the last time we came to a conclusion that the work net is equals to F net delta X. So it means after we've summed all the forces, the net force will be in the direction of the object's displacement, and the angle theta between the net force and the displacement will always be 0. That's why we came to this particular conclusion. Now, let's ask ourselves, the net force is equals to ma. This is our knowledge of Newton 2, to say that the net force is equals to mass times acceleration. So if I'm saying this is my equation 1, I'm gonna call this work net equation 1. Let's call this equation 2. So work net is equals to F net delta X. F net is equals to ma equation 2. Now if I sub equation 2 into equation 1, it means I'm interested in this part. F net is equals to ma. It means where I see F net, I'm gonna put ma. My work net will then become, remember where there's F net, I'm putting ma times what? Times delta X, which simplifies to work net is equals to ma delta X. Let's call that equation 3. Very beautiful stuff. So we just made that substitution there. But now if you look at kinematics, there's a couple of things we discussed in kinematics, such as this equation. Vf squared is equals to Vi squared plus 2a delta X, like that. Very interesting equation. Now if I look at this equation there, there's something that makes you want to smile, because this guy looks exactly like this guy on equation 3. This guy there, this guy there, they look exactly the same. So I'm interested in this equation to manipulate it such that the subject of the equation is a delta X. Let's do that. Vf squared is equals to Vi squared plus 2a delta X. Now if I transpose, I'll have Vf squared minus Vi squared is equals to 2a delta X. Now if I have everything, I will have 1 over 2 Vf squared minus 1 over 2 Vi squared, which is equals to which is equals to a delta X. That's gonna be my equation 4. So if we write it starting from that side, we'll have a delta X is equals to half Vf squared minus half Vi squared. This is equation 4, like that. Very beautiful stuff. So our a delta X is expressed by half Vf squared minus half Vi squared. Now if I sub equation 4 into equation 3, what will I have? Remember, equation 3 is this guy there. Work net is equals to m a delta X. But a delta X, this guy right there, is the same as that guy. So where I see a delta X, I'm going to put half Vf squared minus half Vi squared. So my work net is going to be m, but a delta X is half Vf squared minus half Vi squared. Very interesting stuff. Now I can remove the brackets. I've got work net is equals to half of m Vf squared minus half of m Vi squared. Very beautiful stuff. But when I look at this, I can see that I have half of mv squared. What is that? You remember you said kinetic energy is defined as half mv squared. So what does it mean? It means I'm looking at the final kinetic energy and the initial kinetic energy, and I'm taking the difference. That means I'm saying work net is equals to EKF minus EKI. That means work net is equals to the change in kinetic energy. Work net is equals to change in kinetic energy. And that beautiful story right there, we say this is the work energy theorem, which states that in words, the net work done on an object is equal to the object's change in kinetic energy. The work energy theorem, very beautiful story, states that the net work done on an object is equal to the object's change in kinetic energy.